Okay, we're ready when you are.
Great. All right. Thank you for attending the last lecture of this short course. Today we are going to talk about decoherence, meaning we'll incorporate noise in quantum systems and see how we can deal with this problem in large-scale applications like quantum networks. So I will start off by discussing how we can distribute entanglement using the protocol called entanglement swapping and how we can use that protocol in quantum networks. Then I will move on to noise in quantum systems and how we can differentiate between pure and mixed states. Then I will briefly discuss how we can reconstruct quantum states. This is a process called quantum tomography, and revisit entanglement and talk about how we can quantify this property. And finally, I will conclude this lecture by discussing how we can deal with noise using devices called quantum repeaters in quantum networks, which work mainly based on a protocol called quantum distillation. And finally, discuss an application of quantum networks, which is quite popular, namely quantum key distribution. All right, so last week we discussed about quantum teleportation. This is a protocol where Alice wants to teleport state to Bob, not with direct means. What she can do instead is sharing an entanglement prior to the protocol with Bob, and then she can mix her input state with one part of the entanglement, one part of this state, perform certain quantum operations, perform measurements, collect the results of those measurements, and broadcast them classically to Bob. Then Bob, he can use that information in order to perform an extra set of quantum gates in order to reconstruct the state that Alice had prior to the protocol, and that is what it's called quantum teleportation. Now we'll see how we can extend this protocol. Instead of teleporting quantum states, arbitrary quantum states, we can start teleporting entangled states. This is called entanglement swapping. Now we can introduce another agent named Charlie, and we assume that Alice and Charlie share some entanglement, and also Charlie with Bob shares some entanglement, but Alice and Bob are not entangled with each other. Then, analogously to teleportation, Charlie can perform certain quantum operations and measurements on those two parts of entanglement, then perform measurements, collect the results of those measurements, broadcast them publicly, either to Alice, Bob, or both of them. And then they can also perform certain operations in order to create a new link of entanglement between them. But at the same time, the entanglement that was shared between Alice and Charlie and Bob, now it's vanished. So this is a protocol that was proposed in 1993, and we can think of it as an extension of teleportations, like teleporting an entangled state. So we can use entanglement swapping as a means of distribution of entanglement in quantum network. By quantum network, I mean we have a graph where we have those nodes. Nodes correspond to quantum states, maybe multiple quantum states that an agent can create and distribute. And then we have the links, which correspond to entanglement shared between the two nodes. And in general, the task that we're interested in quantum communication is to distribute entanglement between two arbitrary nodes. For example, let us assume that we want to distribute entanglement between nodes A and F, which, as you can see at the moment, are not currently entangled. However, there are intermediate links that are entangled with each other. So we can start off by performing an entanglement swapping between A, B, and C. That will create a new link between A and C, followed by another entanglement swapping operation among the nodes C, D, and E. That will create another entangled link. And analogously, C and F can be connected with entanglement swapping, and finally A and F. So broadly speaking, that is how we can connect to spatially separated nodes, which were not previously entangled through entanglement swapping. However, so far in this lecture and the previous lecture, we have never discussed about the possibility of a non-ideal system. We were only talking about ideal system where noisy plays no role. As you can imagine, if we have noise, that noise will corrupt the entanglement that is shared, but also we would like to take into account certain imperfections when we perform quantum operations. And that brings us to the second topic of this lecture, which is decoherence. So in general, we assume that we have a quantum system, psi, which we call principal, because this is the state that's the system that we care about. And this system is in general interacting with another system that we call environment. And this is a system that we don't have access to. However, the principal system may interact with it and share information. Information may leak out of the principal system, so we have to take into account those type of interactions. And this is how we can model noise in general using what we call Steinsberg dilation, which is this operation where we have the principal system, we have the environment, and we let them evolve through a unitary transformation. We saw that how it works in the first lecture. And then the outcome will be a state which now it's a global state, takes into account both principal system and environment that we call principal psi. However, in general, this state, capital psi, is in general entangled. Those type of operations, those unitary transformation upon quantum states may create entanglement, which creates a problem because if the global state was separable, it would be easy for us to differentiate between the principal system and the environment after this interaction. Now, when we end up with an entangled state, there is a problem on how we can actually characterize and focus only on a subsystem. So the mathematics that we've seen so far regarding quantum states are not enough to take those models into account. So we have to take a step further. And what we can do is instead of model quantum states with vectors, with kets, as we've seen so far, what we can do is start representing them with matrices. A trivial extension for a matrix state, which is already represented with a vector psi, is to take the outer product of it. Like, for example, if we have a qubit, the two-dimensional quantum state, we can always represent it with a matrix by taking the outer product of it. So we multiply the ket with the bras, and also we conjugate every element of the vector, and we end up with this matrix. Now, if we have a composite system, for example, of two quantum states, then analogously to vectors, we can again model it with a tensor product of those two matrices. Let's see how that works. If we have two matrices, we can always construct the tensor product as follows, where we take the second matrix and we multiply it with each element of the first one. That will give us a higher dimensional matrix. So in general, given two matrices, we can always apply this operation and end up with a higher dimensional matrix. However, analogously to vectors, when we are given with a matrix, it's not always possible to write down as a product of lower dimension matrices. However, given that we take this step and we start modeling quantum states as matrices, we can take advantage of an operation that is called the trace of the matrix. And we'll see in a moment how this is useful and why this is useful. So the trace of a matrix is nothing but the sum of the diagonal elements. However, we can also have the partial trace, and the partial trace for the simple case of a product matrix, X tensor product Y is just Y when we partially trace out the first system, and X when we partially trace the second system. Now, so far, there's nothing interesting because we could do everything with vectors in an analogous way. However, using the partial trace, we can do this similar operation onto matrix that are not necessarily written in a product form. So for example, here when we have an arbitrary matrix M, which is given in this block form, then we can always trace out the first or the second system as follows. And the reason why this is interesting is because we can go back to the problem we discussed on the previous slide and see that given two quantum states that are interacting with each other and creating a new quantum state, which is the S prime AB, we can always use the partial trace in order to trace out either the environment or the principal system. So we can end up with S prime A, which corresponds to the principal quantum system after the interaction, and S prime B, which corresponds to the environment state after the interaction. Which leads us to the point where we have to revisit the postulate that we discussed during the first lecture. We've seen that we said that a quantum system known as a quantum state is represented by a vector. However, we have to update that, and from now on, quantum systems or quantum states are represented by matrices. Now, in particular, those matrices have some properties, and the two basic properties are that they are normalized and positive. By normalized, we mean that the trace of this matrix is equal to 1. That is practically an extension of the normalization convention that we took for vectors for kets. When we normalized quantum states as vectors, we said that all of them should have the same length. In the same way, if we represent quantum states with matrices, we also have to take into account that normalization to keep some consistency. And a matrix is called positive when it has positive eigenvalues. At the moment, that might seem a bit abstract, but I will get into the reason why we have density matrices have this property in a second. Now, if we assume that now quantum states are represented by those density matrices, normalized positive matrices, then we can create two big categories of those states, the ones that we call pure and the others that we call mixed. So pure quantum states are the ones that can be written as an outer product of a vector, and all the rest are called mixed. And the reason why are called mixed is because, mathematically speaking at least, they can be written as the combination of pure states of outer products. Geometrically, we can imagine that as follows. So we can have a set of all possible quantum states. Every state which is within this set is a mixed state. For example, we have a mixed state S, and every state at the edge of the set can be thought of as a pure state, and we can combine those two in order to create a mixed state. And by combine, I mean that we have those coefficients P1 and P2, which correspond to probability distribution. And that is, by the way, the reason why we define density matrices as the ones which are positive, because by construction, those probabilities would be positive numbers, which correspond also to the eigenvalues of this matrix. And finally, let me note that a mixed state can be written as a combination of different pure states. For example, we can have a different decomposition as follows. And regarding the evolution, we have to update that expression as well. We saw on the first lecture that a quantum state represented by a vector is evolved unitarily by having a unitary matrix applied onto it. When we discuss about density matrices, then as you can see from the outer product, I hope it's obvious that we're gonna need also to complex conjugate the unitary transformation. So the result would be, we have that expression. So we have a quantum state S, and the evolution of it will be described by this expression where we have to multiply U and U dagger. In order to give an analogy on what exactly is happening and why we call it mixed states, maybe a nice classical analogy would be the spectral colors, meaning the colors that are associated with a specific wavelength. And even though, so we have all those colors, however, we cannot find white in those colors, or there is no magenta in there. And the reason is that those type of colors can be created as a mixture of the spectral colors. For example, white can be created if we mix evenly blue, green, and red, and magenta can be created by mixing up blue and red. So in general, we can think of it as having two types of colors, spectral and non-spectral. Spectral are the ones that correspond to wavelengths, and non-spectral, the ones that correspond to mixture of the spectral colors. And the analogy is trivial here. Pure states can be thought of as the spectral colors, and mixed states as the non-spectral ones. And so far, we did all those this extension in order to take into account noise. And as we discussed during the first lecture, when we talk about interpretation of quantum states, sometimes we can always think of quantum states as the ones that are ideal, those vectors, those kets, but we would like to incorporate those, the noise. And we would like to see how we can actually construct those density matrices, those mathematical objects in practice in the lab. Now, we know that it is impossible to determine the unknown quantum states of a single quantum system by any measurement or any sequence of measurements in order to reconstruct to any density matrix for a quantum system. So in other words, in order to associate a density matrix to a quantum system, we need to perform statistics, meaning measurements, on an ensemble of identically prepared quantum systems. So we have to perform measurements onto different observables of the quantum system. Since we invoke the term statistics, of course, we're gonna have to start measuring mean values of observables. Let's remind ourselves that the mean value of a random variable in classical statistics is given by this expression, where xi is the value of a certain event I, and p of xi is the probability of that event to happen. Now, analogously, in quantum mechanics, the mean value of an observable is given by this expression, where now xi will be the outcome of a measurement, and pi will be associated with the probability of that measurement to happen. So we've seen that mathematically, this density matrix, this object that corresponds to quantum states, is represented by this decomposition of a mixture of pure states. But in practice, in the lab, the way we can construct those objects is by performing measurements on observables m and measuring the mean value of them. So the more the larger the ensemble that we have, and the better the measurements that we can perform, the more refined will be this object. And then we can even, regarding interpretation, we can either assume that there is an ideal quantum state and we're just approaching it with more and more measurements, or we can take the more agnostic position and say that we just have a certain quantum states, quantum system, an ensemble of them, and we perform the measurements that we can perform, and then this will be, at the end of the day, the quantum state that we have to deal with, which will be practically a mixed state. Now, to make that more concrete, if we are talking about qubits for two-dimensional systems, then the observables that we have to measure and create the mean values of them would be the Pauli matrices. If you remember, during the first lecture, we gave the correspondence between quantum states and Wigner functions. We said that a quantum system can be represented either by one or the other entities. So probably now things make more sense, because we can see that this density matrix exists in this expression for both of the Wigner functions for discrete and continuous variable states. And maybe now it's more obvious that at the end of the day, what we have to do is to recreate this function that corresponds to the system. In general, this process of reconstructing the quantum state is called quantum tomography. This is a field that was pioneered by Professor Raymer's group back in the 1993 and 94, who Professor Raymer is also part of the Center for Quantum Networks. Having now this knowledge, we can start off by assuming that the input state is a pure state, and also we can assume the same thing for the environment. And in general, now we can incorporate noise by considering this unitary operation. And in general, the output state after this operation will be a mixed state. The exact same operation can be thought in a more compact way as having an input state and an output state, and everything else can be seen as an entity that we call quantum channel. Also, going back to this approach where we have the set of states, we can also think of the exact same scenario as having a quantum state, which is pure, so it's at the edge of this set, and the more noise we have, that we go towards the center of the set. And this is something that is called decoherence for the following reason. Coherence is a different term for superposition, and as the state becomes more and more mixed, we end up having a system that the effect of superposition is less impactful, or even if we go to the extreme, we have a completely mixed state, then there is not even a superposition, this effect, this phenomenon that we discussed. So we say that the system got decohered. Let's see an example to understand exactly what's happening. We can assume that the input state of the principal system and the environment are both pure and are this outer product of state zero. And as the interaction, we can assume that we have those two unitary operations, the Hadamard and the control knot. Those are the gates. If you remember, that was the way we created entanglement during quantum teleportation. That was the way we created the resource states. Now, in this density matrix approach, we have this expression for the Bell state, that is the maximally entangled state for teleportation. However, that describes the global system. That describes both, in this case, the principal and the environment system. However, if we only care about the principal system, what we have to do is to partially trace the environment. And if we do that, we end up with this matrix that now corresponds to the subsystem of the principal system after the interaction. And we would like to have a way to differentiate between mixed and pure states, given a quantum state, to know whether it's pure or mixed. And we can actually do that. There is a criterion, because we have a condition for pure states, which says that the trace of the square of a matrix is given to 1, and anything else is a mixed state, meaning that this expression can go from 1/2 to 1. So in other words, we can use that expression to define the purity of a certain state. However, the take-home message here is that noise decreases the purity of a quantum state. So the state becomes more decoherent, or in other words, the purity drops down. So it increases the mixedness of the state. Also, if we move on to entanglement, we have to revisit that part as well, because now we have changed the description a little bit of the states. If you remember, we only had the case of uncorrelated and correlated systems for the vectors. Now we represent as density matrices. If the system is uncorrelated, meaning that the subsystems are described by, the whole system is described as a product of the subsystems, then this is by construction a separable state. However, if we have a quantum system that cannot be written as a product of the individual subsystems, then there are two cases. The system might be either classically correlated or quantum correlated. By classically correlated, we mean that the density matrix can be written as a combination of product states, and this is also denoted as a separable state. Otherwise, if we talk about quantum correlated systems, then we end up having entanglement. Now, given an arbitrary quantum state, it's a really hard problem to identify entanglement. In other words, creating separability or entanglement criteria is not an easy thing unless we make some simplifications or we care about systems of low dimensions. As you can imagine, if it's hard to identify entanglement, it's even harder to quantify entanglement. However, there is a whole field of in quantum information called entanglement theory, where it deals with those two specific problems. And today I will try to give you an overview of how we can in general quantify entanglement. There are two big categories of measures, ones that we call geometrical and others that we call operational. Geometrically speaking, we can imagine having two sets of states, the separable states and the entangled states. Now, this is not a Venn diagram. That does not imply that separable states are a subset of entangled states. You can think of it as the entangled state is a set that there is a hole within them, and we have the separable states there. And given a quantum state S, which is somewhere in the entangled region, then the question that we can ask is, what is the minimum distance of this state to the set of separable states? Now, depending on how we measure distance, we can create different measures. For example, if we decide to measure distance with the relative entropy, then we end up with a measure called relative entropy of entanglement. On the other hand, we can have operational measures for entanglement, meaning that given the system that is represented by quantum state S, if we assume that we have M of those systems and we have N Bell states, which are the maximally entangled states, then the question that we can ask is, what is the minimum amount of Bell states that we need to create that state? And this is a measure that we call entanglement cost. So we try to minimize this ratio between Bell states and the states that we are interested in. And the reason is that Bell states are so important in quantum information that we can use them as a reference frame. So we can ask, we need to know what is the minimum amount of them that we can start off to create it. Or we can think of this problem from a different perspective. We can ask a different question of, given now this set of this state S, using only local operations and classical communications, how many of those Bell states we can create? And this is called the distillable entanglement. Now, as I mentioned, there are a lot of different ways to measure entanglement. Those three are just three that are pretty popular and well-known measures in the literature. However, this review letter by Horodecki family introduces a lot of measures, discusses a lot of different measures and ways to identify entanglement. And similarly to the purity of the states, regardless of how we decide to measure entanglement, we know that noise monotonically decreases the amount of entanglement. And given that problem, we move on now to the last part of the lecture, because we have to deal with this noise. So far, the question was how we can distribute entanglement between the nodes A and F, but now we can assume that every link which corresponds to entanglement in the nodes in between does not correspond to a Bell state. So it's not a perfectly entangled state. The question is now, if we want to perform a protocol between A and F, what can we do to increase the amount of entanglement? So a way to do that is by using devices that are called quantum repeaters. So let's see how a quantum repeater works. A quantum repeater, if we zoom in into this sketch, we can imagine it as having the nodes sharing entanglement with the repeater, but it doesn't mean that we only have one entangled state. We can have at the same time multiple entangled states shared between them, and all those entangled states are not maximally entangled. So then we can use a specific operation that is called distillation, which performs operations, local operations onto each part of the entanglement, both in the repeater and the quantum nodes. And using this technique, we can distill entanglement, meaning that we can create a less amount of entangled states, which, however, have a better quality. And if we can keep doing it, then ideally we will end up with a single entangled state, which is maximally entangled. Now, entanglement distillation, which is also called entanglement purification, is a probabilistic technique. And that is the reason why we start off with an ensemble, a big set of entangled states, because during this process of distilling entanglement, some of entangled states will be discarded. So because this protocol might fail. So we have to start off like with an overhead there. Also, quantum repeaters are not they do not only involve entanglement distillation. In a quantum repeater, we can imagine having quantum memories. Those are devices that can store entanglement for a longer period in order to use that at a later states. And second and third generation of quantum repeaters also borrows certain techniques from the quantum computing field. So there are error correction codes that can be also performed in a quantum repeater in order to further boost their performance. Let us see a specific example to see how that could work. So we can imagine having the simplest case of having just two quantum states represented by this expression we call Bell diagonal states. Those Bell diagonal states are the mixture of all the four possible Bell states. So in general, this S is a mixed quantum state. And in order to distill entanglement, we let Alice and Bob perform operations, meaning that they perform phase shifts and control node operation. And then they measure only the second qubit. Now, whenever both of them either measure 0 or 1, then this is a successful entanglement distillation process. Otherwise, if they don't measure those results, then they discard it, and they have to do that over and over and over again. However, when the distillation is successful, then this part of the Bell diagonal state will be increased, meaning that the coefficient will go towards 1. So if we keep doing that for a lot of times, then ideally this Bell diagonal state will converge into this specific Bell state. So we will end up having a maximally entangled state in order to perform the next operation, which might be teleportation or anything else. And finally, we started with a discussion of how we can distribute entanglement and how we can deal with the problem of noise in order to perfectly distribute entanglement between two spatially separated nodes A and F. However, then the question might be of why do we even bother doing all these processes? Why do we care about distributing entanglement in a quantum network? The reason is that there are several applications that we can use those quantum networks for. The three more prominent ones are regarding quantum cryptography. We can do quantum computing, meaning like distributed quantum computing or cloud quantum computing on them, or quantum sensing. I will focus here only on the first one because it's by far the more mature application for quantum networks. One of the first that it was discussed regarding quantum communication, in order to see why it would be great to have those quantum networks and how and why we spend so much time doing research on developing better and better quantum repeaters. So before discussing quantum cryptography, let's set the base and let's see what cryptography is all about to begin with. So we can assume that having Alice and Bob, and they want to securely communicate a specific message. So this message can be represented by those bits, the zeros and ones. This is what Alice wants to send to Bob, and she can use a certain key, meaning that another series of zeros and ones that she can add up to the message in a binary form, and then create an encrypted text. Now, this encrypted text is sent to Bob through a public channel, and Bob, using the exact same key, he can also perform a sum operation, a binary sum operation between key and the encrypted text. And that's how he can retrieve the message that Alice sent to him. By the way, this is what is called one-time pad protocol in quantum cryptography. And it has been proven by Claude Shannon in 1949 that in order for Alice and Bob to securely communicate, they need to satisfy 4 conditions regarding the key. So the key needs to be the same size as the message. The key has to be used only once. It needs to be random, and it has to be distributed to both parties in a secure way. Now, as you can imagine, the first 2 conditions are really easy to satisfy. That's not a problem. We can do that classically or quantumly. That's not a big deal. Regarding randomness, that's a bit more tricky because it's hard to define what is a random key. Also, however, in practically speaking, creating a random or pseudo-random keys is not a big deal. We can do them classically quite efficiently. It's true that we have also quantum randomness generators that in principle they can perform better. However, this is not a big problem to cryptography at the moment. The big problem is how we can distribute securely the key between 2 parties. Currently, classical cryptography deals with this problem using certain computational problems which are pretty complex to solve. For example, the factorization of a big number. So we create certain passwords that Alice and Bob have to use in order to distribute this key. However, the assumption is that those passwords are just extremely difficult computationally to be broken, but that always leaves the possibility that at some point we will find a way to break them. It's not proven that are unhackable by construction. And that is where quantum mechanics can offer a new way to securely distribute keys with an operation that is called quantum key distribution. Let's see how that works. So I will talk about the protocol that was described by Bennett, Brassard, and Mermin back in 1992, which is a modification of the protocol that Arthur Eckert proposed in 1991. And we can assume that Alice and Bob share a set of entangled states, which are correspond to the Bell state, which is the maximally entangled one. If you remember, last week we saw that a Bell state can be represented in different bases, different orthonormal bases. For example, we can use the orthogonal vertical or the diagonal anti-diagonal. In general, we can describe a Bell state using up to three mutual unbiased bases, but for the moment, 2 is enough to show how quantum key distribution works. So for the sake of this example, let's assume that Alice and Bob share only 10 entangled states. And as soon as they got the one part of this entangled state, then Alice and Bob start performing measurement in different bases that they decide without knowing. They practically decide randomly. They just get up states and they decide at that point if they're going to measure it in one on the other basis. And we can do the same for all the 10 states. Now, they don't know in advance what they might do. They also don't know what the other person is doing. Now, as soon as they make this decision and they actually measure the quantum state, the state will collapse in one or the other state, which depends on the basis. At this point, Alice and Bob can classically communicate and share information not about the observations that they got, but only about what basis they perform those measurements in. And if they do this, they can discard all the cases that they observed, they perform the measurement in different bases, and they can keep only the ones where the bases were the same, which are indicated here with a red color. And as you can see, whenever they measure the states in the same basis, since the state is perfectly entangled, the results are perfectly correlated. Practically, that implies that if we associate 0 with vertical and diagonal states and 1 with orthogonal, horizontal and anti-diagonal state, then they can immediately create a key between them, shared between them, which is identical, and then they can use that key in order to perform cryptography. However, as you can imagine, that is the ideal case where they share a key and nobody else is trying to intervene and steal information. However, the whole point of doing cryptography is to take into consideration the case where there is somebody in between trying to steal information. So we have to move up to the situation where we have an eavesdropper named Eve in this case, who can be in the middle between Alice and Bob, and without them knowing, she can take one part of this entangled state and she can measure it in order to get information about this key. However, at this point, we have to take into consideration an important result in quantum mechanics, which is practically the basis of QKD, of quantum key distribution. We have to take into account the so-called no-cloning theorem. The no-cloning theorem says that a quantum state cannot be copied, cannot be cloned. There is no unitary transformation that can given an input state psi and an ancillary state phi, that will end up giving us a copy of this state psi, which practically means that if Eve intervenes in that communication scheme and collects perform measurements on the entangled state, she cannot copy that state, perform measurements on one, and send the other to Bob. So she has to send Bob a different state, which will be, the best case scenario will be to just send the state that she measured. Let's see how that works. Now we have the same scenario as before, plus the Eve's basis and observation. We can assume for simplicity that Alice and Bob decided to measure at the same basis as they did before. But now we have also Eve, that she decides to measure on certain bases. Remember that Eve is in between, and whenever Eve is performing measurements, she doesn't know in advance what Bob will end up measuring. So she has to make a guess regarding the basis that she will measure. All right, so then at this point, we have Alice and Eve collapsing their states at that point. And since now Alice and Eve are the parties that they share entanglement, whenever they happen to measure in the same basis, which is the case indicated by blue, then their corresponding observation will be perfectly correlated. Now, Eve is at this point that since he couldn't copy the states, he has to just send something to Bob and try to conceal her presence. And what she can do is just probably send the state that she just measured. So, now with this pink line, those observations, this is the observation of Eve, and regarding Bob is the input state that he gets. However, if you notice, there are cases where Bob decides to measure on the same basis as Eve, and then Bob's output state will be the same as Eve's state. However, there are cases like the third and the fourth state where Eve is sending him a state, but Bob is deciding to measure on a different basis, which practically means that the actual observation of Bob will be a bit different to what Eve observed. Now, at this point, Alice and Bob will start communicating publicly and sharing information about which basis they made their corresponding measurements. And as before, with red here, we have the cases where Alice and Bob bases are equivalent. At this point, in order Alice and Bob to check whether there was an eavesdropper in the scheme, what they can do is not just compare the bases that they measured their states on, but they can also compare observations. And if we can see there, in this case, they can end up having those discrepancies, observations that are not equivalent. However, they would expect them to be identical since the assumption was that they share an entangled state. So this is how quantum key distribution can help in order to detect the presence of an eavesdropper out of a huge sample of quantum states. Alice and Bob can always start off by sharing information about the basis and take a certain chunk of those states and also make an extra announcement about the observations to make sure that there was not an eavesdropper in between. So in other words, quantum key distribution does not help to communicate the message per se. Eve doesn't get any information for the actual message. Quantum key distribution only helps to find whether there was an eavesdropper or not. And with that, that was all I wanted to talk to you about in this course. Let me also wrap up this course by getting back to the basic question that we asked during the first lecture to answer the question of what is quantum mechanics. I really like this quote by Scott Aronson, who said on his book that even though it was discovered by physicists, it's not a physical theory in the same sense as electromagnetism or general relativity. In the usual hierarchy of sciences, with biology at the top, then chemistry, then physics and math, quantum mechanics sits at a level between math and physics that I don't know a good name for. Basically, quantum mechanics is the operating system that other physical theories run on as application software, with the exception of general relativity, which hasn't yet been successfully ported to this particular OS. There's even a word for taking a physical theory and porting it into this OS. We say that to quantize. All right, and with that, I would like to thank you for your attendance, and I'm really happy to take any questions.
Okay, stupid question. When the QKD systems exchange observations, how do those observations have to be exchanged securely? How do you do that?
So the observation, they can share it publicly because they only want to check whether there was an eavesdropper or not. So they don't really care at this point if somebody is listening to them or not, because that's all for the check.
Don't care if they listen, but they do care if someone is able to modify what they just claimed. If someone else was able to insert their own basis, they can break the entire system.
That is true, but there's the implicit assumption in QKD that the two parties, Alice and Bob, they we say it's they authenticate the channel, meaning that they know who is who and they can just publicly communicate. But we should think quantum key distribution as an attachment to the classical cryptography, where we still can use certain classical methods in order to perform cryptography and secure the links. But at this point, we can make the assumption that they can communicate publicly, or they can just meet up later and make sure that what they claim to be is true.
So you're saying QKD is secure, assuming that classical crypto is secure?
No, so we assume that Alice and Bob can authenticate themselves. So they always start off by classical means and making sure that they can publicly communicate. And after that assumption, then we can use quantum mechanics in order to make sure that Eve is not in between. But quantum key distribution cannot work just by itself. We still need to use classic cryptographic means. The only difference between quantum and classical cryptography regarding the distribution is whether we use a computational problem, a complex computational problem, to check whether there was an eavesdropper or a physical motivated problem. So in classical cryptography, the assumption is that an Eve cannot break this pretty hard problem of factorization, for example, where in quantum mechanics, we assume that given that we have the no cloning theorem, which is in a sense more fundamental, then this is how we can prevent the hacking of that may happen in between.
So is it worth, Spyros, is it worth mentioning to Scott that when Alice and Bob exchange, say, 1 million potential key bits, they do so securely, then they take only a small fraction, say 5% of those, to compare publicly, and they take those at random. And so only those 5% are public, and then they throw those away, and they only use the remaining 95%, assuming that their sampling of those 5% was unbiased.
Exactly, and even if we assume that Eve is then intervening and changing even those observations that Alice and Bob measure, since Eve doesn't really know what are doesn't have access to this copy of entangled state, even if she just start changing those observations to them, at some point they will end up with certain discrepancies, and that discrepancies will reveal her presence.
And the other point is that if the amount of discrepancies is under a certain threshold, say 10%, they can do classical privacy amplification and error correction, and they end up with a smaller key, but you can prove asymptotically that it is secure.
Do we have any more questions?
I don't know if you know the answer to this question, but you probably have heard that the US government has announced that they do not plan to use quantum cryptography in the near-term future as the go-to solution to ensure privacy or encryption. Did you have any insight into, I mean, I've read the report, what they wrote, but did you keep up with that story? Did you have any insight into why they're not doing that? And I know they're using post quantum encryption methods. Do you know much about that story?
I think the main argument is that in order to start using QKD, we have to change the infrastructure. So quantum computers can indeed break the factorization problem, but there are other problems in cryptography that are not hackable by a quantum computer. So they can still use in the same infrastructure and change the problem that they work regarding they use regarding cryptography. So this is I think like a financial issue that moving to QKD will have to change a lot the infrastructure. However, that takes into account the discrete variable quantum key distribution, because in continuous variable QKD, the main point of it is that we can still use the current infrastructure. However, CVQKD is not as well developed as DV at this point, so probably that is an issue. But it's true that the US, it's not investing that much in QKD, at least not as much as China and Europe.
Mhm.
Yeah, another issue that they brought up is the potentiality for side channel attacks against real QKD systems.
Yeah, I think that's right. It's worth mentioning that the position of the CQN is not that QKD is going to be an outcome of the quantum network, but rather it's like a test bed. If you can't run a QKD system under ideal conditions, then you certainly cannot do entanglement distribution across the same network, which is the ultimate goal.
Any other question? All right, if not, thank you all for the attendance, and thank you for being part of this short course.
Thank you, Spyros. It was very nice.
Thank you, Spyros.
My pleasure.
Thank you for presenting what must be to you some really elementary material.
But well done.
Thank
Yeah,
you.
if we can't explain this stuff at a simple level, that means we don't understand it, right? That's right. Okay, see you later, Spyros.
Yeah.